Hello and welcome back. So, we are going to look at the simplification of the first law, the general form of the first law for various processes. So, the first law for a control volume, so we wrote it as something like this. So, we have the change in energy with respect to time is whatever heat which is coming in minus any work which is going out, plus we said any mass which is coming in brings along with it some energy plus the flow work which is enthalpy, plus we said there is kinetic energy which is given as this, plus whatever is the potential energy at the inlet minus whatever is going out. So, if we have more than one exit, we have a sigma here, and whatever is going out is taking along with it energy and flow work which is enthalpy, plus it is taking out kinetic energy, plus we have it taking out potential energy. So, this was the general form of the first law for a control volume. What we can see is that we can simplify this in various fashions. Of course, one of the easy simplifications is to look at it when there is no mass coming in or going out. So, if there is no mass going in or going out, then essentially what we get is that if there is no mass coming in or going out, then this is 0, this is 0, we get this, which was essentially our first law for a control mass. And if things are steady, nothing is changing with time, we would integrate this and get essentially this, which was the first law which we were writing earlier. So, what we see is that our first law for a control volume is actually the more general form. So, we can simplify it and get back all the other stuff we had. So, now that we know this, the remaining things can be derived back from this expression. So, this is the expression which is sort of worth remembering more than the other ones we had, because we can get back everything else. So, we had no inlets and outlets, we have a control mass, then this is the rate form for a control mass. If things are steady, we can integrate this with respect to time, and then we get this, which is what we had earlier. We can also look at simplifications for some other processes, one of which is commonly given in textbooks as a steady state, steady flow energy equation. I would still recommend that you just remember the first law in its general form, because all of these simplifications are very easy to do. So, in this kind of an expression, what we are assuming is that the state of mass at each point in the control volume does not change with time. So, what we are assuming is steady state, which means that nothing is changing with respect to time. So, steady state means things are constant with respect to time. We are assuming that the control surface mass flux and state of mass does not vary with time, and we are assuming that rate of heat and work transfers are constant with time. So, we are assuming everything is constant with respect to time. So, a general equation which we had is essentially the first law for a control volume. I am not going to write the subscripts control volume, because we are dealing with control volumes here, and we know that if there are no masses going in or out, it can also be brought back to the control mass or system form. So, we had a sigma here, I will skip that for the moment, but we know that if there is more than one inlet and one outlet, we need to put sigma over here, or maybe I will put it anyway, it does not really matter. So, we have internal energy and flow work together, which is enthalpy. We have kinetic energy, and we have potential energy at the inlet minus a similar form. We will have enthalpy at the exit, kinetic energy at the exit, and potential energy at the exit. If we assume that this is a steady process, then it means that then nothing changes with respect to time. So, it means energy does not change with respect to time, or the final energy is equal to the initial energy, or essentially this term is 0. What we are assuming is that q dot and w dot do not change with time, but they are both there. So, individually they are not 0, even in terms of summations they are not 0. So, q dot does not change with time essentially means something like, for example, the rate of heat transfer is 100 watts. So, q dot is not 0, but the value of q dot is not changing. Q dot is 100 watt, it is not changing from say 100 to 150, it is remaining at 100. That is what we mean as rate of heat and work transfer are constant. So, W dot is constant, say the system is doing 50 watts of power. So, it is not 0, only thing is that value of 50 is not changing. So, now that we have this gone, so essentially the equation is left with the remaining terms. So, that is essentially what we have. So, all we did is note that this term becomes 0, and we said that these two terms are not varying. We can have also other simplifications here. So, since nothing is changing with time, the mass flow rate which is coming in must be equal to the mass flow rate which is going out, because from mass conservation we also have this other expression dm by dt is m dot I sigma m dot I minus sigma of m dot E, which is our mass conservation. So, we have energy conservation, we also have mass conservation, which is this expression. What is generally assumed in these cases, even though it is not explicitly written here, is that we have only one inlet and one outlet. So, if there is more than one inlet and more than one outlet, we need to use this expression in this form, and this term becomes 0, but we can use this expression in this form. This is the simplification we can make. But in many of the systems we have only, for example, one inlet and one outlet. If there is only one inlet and one outlet, then I do not need the sigma here anymore, because it is sigma over 1 essentially. So, I do not need this anymore. So, that is a simplification which we can make. Assuming only one inlet and one outlet, this is a simplified version of this. If there is only one inlet and one outlet, then this expression tells me that m dot I minus m dot E is 0, which means m dot I is essentially equal to m dot E. I can call this as some other m dot. It is the same, I equal to E, I can remove the subscripts. So, in that condition, I can essentially remove this subscript over here, I get m dot into this. And what I can also do is I can divide by m dot over all of these terms. So, I get 0, this term is 0, q dot by m dot is the specific heat transfer, w dot by m dot is the specific work, and I have plus whatever is in this bracketed terms. So, assuming that things are steady and there is only one inlet and one outlet, my first law for the control volume has become simplified to this expression, which is often used in many cases. But as I said earlier, the simplifications are very simple. So, all we did is knock off this term, found out there is only one, if there is only one inlet and one outlet, we said the sigma can go, and these two can be represented by a single m dot. So, many books spend a lot of time talking about these equations and their applicability. What I would recommend is that we stick to this equation here, because it is general form and it is very easy to knock off terms in this depending on the conditions we have. So, even though I have written this here, I am going to keep going back to the first expression every time we look at a process. There are many examples of processes where we can use this first law. So, one of them is what is called as an adiabatic throttling process. So, for example, if you have liquid flowing in a tube and you have a very thin section for the tube, then essentially there is a lot of pressure drop in this tube, and that is what we call as a throttling process. So, we usually have a very long, this is not shown completely, this is to say that this tube is extremely long. So, you have a very long and thin tube in which you push a flow. During that process, what happens is that there is a lot of drop in pressure. If the fluid which you have is a non-ideal gas, so for example, if you have something which is very far away from ideal, then what will happen is during this process you have usually a drop in temperature if you are in the right conditions, and that is one of the ways in which we usually have refrigerators working. We push some liquid through a long tube, the temperature drops and it becomes cold fluid, and we use that cold fluid to actually cool whatever substance you want to keep inside the refrigerator. Another example of this would be, for example, you have a pipe like this and you have some kind of a valve. as you turn this valve, this thing comes down and blocks the area available for the flow. This is also what we call as a throttling process. So, we can write the first law for this kind of a throttling process. So, the first law, the general form we had here for a control volume, we are going to treat all of these things as control volumes because there is flow. There is liquid flowing through these. So, we need to use the control volume analysis. So, we have Q dot minus W dot plus we have sigma Mi dot into enthalpy, which represents energy plus the flow work, plus we have the kinetic energy, which we are writing as some Vi square plus 2 plus potential energy at the inlet. We have minus whatever is going out. So, we have this kind of an expression. If there is more than one inlet, you would also have sigma. This is a process of flow going through a pipe. For most cases, this process can be assumed to be a steady state process. So, if we assume this to be at steady state, this would be 0. In an ideal throttling process, we expect this to be adiabatic. We do this in an insulated pipe. So, in an ideal process, this would be 0. We do not have any shaft here, we do not have any electrical work here, we do not have magnetic work here, we do not have surface tension work here, and so on. The only work actually done here is in pushing fluid in and pushing it out. Those terms of work, flow work, is already taken into account in this. So, we do not have any other forms of work. This pipe itself is not deforming, it is rigid. So, there is no PDV kind of work, there is no displacement work, there is no other shaft work or any kind of work. So, we do not see any scope for any work to be done here. So, therefore, this term is 0. There is only one inlet and one outlet. So, I can get rid of the sigma. Since all of this is 0, I can have from mass conservation, I anyway have this. It is steady state, that means anything which is divided by dt should be 0, that means this is 0, which means m dot I is equal to m dot E. So, that is equal to some m dot. Since all of this is 0, I can also divide by the m dot. So, I take this m dot to the other side, I divide everything by m dot, this is 0 by m dot. So, they are all zeros anyway. So, I am left with this. In most of these cases, there is not the change in potential energy is usually very small. So, what I am left with this expression over here. I will just write it in this form, I will take all of this to the other side. We are left with something of this kind. I have taken some of these, I have taken these also the other side and taken all of these to the other side. I get an expression of this kind. So, I have the enthalpy at the inlet is equal to the enthalpy at the exit plus change in kinetic energy plus change in potential energy. In cases where the potential energy change is small, which is usually the I do not have Ze square by 2, I just have Ze minus Zi. So, in most of the cases, what we see is, for example, if it is horizontal, there is no appreciable change in Z. Even if it is vertical, these devices, if I had a device like this, for example, maybe it is so tall, so there is no appreciable change in potential energy. So, this term is approximately equal to 0 for most cases. In some cases, the kinetic energy at the inlet and outlet can change, but for the time being, I am going to make the assumption that those changes in kinetic energy are small. What we will see is that, for example, if we look at say values of steam or look at values of ideal gas, what you see is usually enthalpy is much higher than changes in kinetic energy unless velocities are very different. So, for a first cut approximation, if I knew these values, I can take them into account. If I do not know anything about the values, for a first cut approximation, I can assume this also as 0, which tells me that enthalpy at the inlet is equal to enthalpy at the outlet, or essentially change in enthalpy is 0, or essentially enthalpy is constant. So, what we see is an adiabatic throttling process is a process, at least an ideal adiabatic throttling process is a process where the enthalpy remains constant. So, in this device we would have the pressure dropping from left to right when the flow is going from left to right, but we have the enthalpy remaining constant. There is no work done, there is no heat transfer, changes in kinetic energy and potential energy we have ignored, and in such a case the enthalpy still remains constant in an adiabatic throttling process. We can see similarly what happens in other kinds of processes. We saw pictures earlier of turbines and compressors. So, we have for example a turbine. This is the turbine over here, and here this is a turbine. So, a turbine is a device in which we are sending in gas which is usually at high temperature and high pressure. We are letting those gases expand, and in the process of expansion we are trying to extract work by having those gases rotate this device. So, that is essentially a turbine. So, we have high pressure, high temperature gas going here. We are increasing the area so that the gases can expand as they go, and as they go, these are blades which are on some shaft. We have these blades being rotated by the gases because of the angle in which they are oriented, and because the gases rotate the blades, the entire shaft is rotating, and we can attach something to the shaft and extract work. You must have seen this at some point of time. For example, if you have seen an exhaust fan which is not running, so it is switched off, and sometimes air is flowing and it makes this fan rotate on its own. So, the air has energy, it is transferring that to this fan and making it rotate. So, a similar thing is what happens in a turbine. So, you have hot gases which are coming out, which are rotating the turbine. So, we usually indicate it by something like this. We have this diverging section to show that the gases are expanding as they go out, which means that the density will become lower, specific volume will increase, and we have a shaft here to show that there is some kind of work being done. So, we can write the expression of the first law in a simplified fashion for this. The general expression of course is the same as earlier. We are going to always start off with that. We have change in energy of the control volume is Q dot minus W dot plus whatever is the mass which is coming in, the mass flow rate brings in energy, okay. I wrote it in a slightly different fashion here, does not matter. So, in an ideal turbine, this process we expect it to happen at steady state. So, this machine is going to run for several hours, there is always stuff coming in and always stuff going out. So, we would expect steady state to be the condition, except when it is initially starting or finally stopping, we expect it to run more or less in steady state. So, anything which changes with time should be 0. So, this term is 0. In addition, we always have mass conservation. So, it says change in mass with respect to time is whatever is coming in minus whatever is going out, rate at which is coming in minus rate at which is going out, and since it is steady state, this should also be equal to 0. So, we have sigma mi dot equal to sigma me dot. If we have only one entry and one outlet, then we said that we can remove the sigmas, and then mi dot is equal to me dot equal to some m dot, which we have done in the previous cases also. So, I am assuming there is only one inlet, one outlet, so I will get rid of this. So, I am left with this. In the ideal turbine, I do not want any losses to the atmosphere in terms of heat. So, for the ideal turbine, this is 0. The turbine does work That is the whole idea of a turbine. So, this W dot is not 0. This Mi dot is equal to M dot, Me dot is equal to M dot. I can write this. Now, I have the remaining terms. If the turbine is not very large, then changes in potential energy are 0 or are very small. So, each of them may not be individually small, but the change is often small in the case of say gas turbines. In the case of say liquid turbines or hydraulic turbines, we will see that this change may not be necessarily very small. At least in the case of gas and steam turbines, this change. So, individually they are not 0, but G into Zi minus Ze. So, I can have this turbine at a height of say 100 meters from the ground. So, Zi is 100. So, G into Zi is not 0. But if I have the inlet at 100 meters and the exit at 101 meters from the ground, then Zi minus Ze is only 1 meter, which is, so G is 9.8. So, the value of this would be about 10 meter square per second square, compared to like say a power of 100 meter square per second square, specific power. So, in terms of the difference, this value is usually small. So, combined this goes to 0. Similarly, the inlet and outlet have kinetic energy. They have to have velocity because you cannot push in fluid without velocity, but the change in velocity is usually small. So, this change together, so individually they are not 0, but if I take this term and this term together, then both together the difference is approximately 0. So, similarly here this and this taken together, the difference is 0, though individually they may not be 0. So, then I am left with W dot, which is what I want to find out. So, I take this to the other side, is M dot into enthalpy at the inlet minus enthalpy at the exit. So, this gives me the work or the power produced by the turbine. So, if I knew M dot, for example, if M dot is this value, if I knew the enthalpy at the inlet and the outlet, then I can find out what is the power generated by this turbine. So, this would be the power. The specific work is W, which is essentially, sorry about that, W dot divided by M dot, which would be essentially change in the enthalpy from the inlet to the exit. That would be the specific work done by this turbine. So, this was for the turbine. We can also look at it for the compressor. You do the same analysis, we will get the same expression. So, the only difference is in the case of a turbine, this system is doing, or this control volume is doing work. So, we would have inlet at high enthalpy, exit at low enthalpy, and work would be positive. In the case of a compressor, this part is what we call as a compressor. Over here what we are doing is we are rotating this device and it is pressurizing the air, similar to the fans we have at home. So, we have a fan, we are giving it electrical power and it is pushing the fluid. So, in that case what we would see is that the work for this control volume would be negative, because we are giving power from some shaft or from some electrical motor. So, the work would be negative. So, the inlet enthalpy will be small, exit enthalpy will be large. So, this is going to be small, this is going to be large. So, this difference would be negative. So, we see that for the control volume it is negative work in the case of a compressor, because we are doing external work on it, and in that process we are increasing the energy of air. Whereas, in the turbine the fluid is coming in, and what is happening is that the turbine is extracting work and giving it out of this control volume. So, there we see that the work is positive. We can also see what are called nozzles and diffusers. So, for example, a nozzle, say this portion is a nozzle, it is something which has a reducing cross sectional area, and we are trying to increase the velocity of the flow. This would be a diffuser, where we have an increasing cross sectional area and we are reducing the velocity of the flow. let me just take a moment to also show that this is what we would use as a designation for a turbine. For a compressor, we would draw it the other way. So, this would be a compressor. As we compress a gas, its density becomes higher. So, the area for the flow, if we take for example rho AV is the mass flow rate. As we compress, we are changing the density. If the density becomes higher, we need a smaller area for the flow to go out if the velocity is the same. So, we would designate a compressor in this kind of a fashion, we designate a turbine in this kind of a fashion. So, the gas is becoming denser here, the gas is expanding here, here it is being compressed, here it is expanding in a turbine. Similarly, we have a diffuser where there is no shaft work, but we are having an increase in area, and a nozzle where there is no shaft work, but we have a reduction in area. So, we can see the expression of the first law for nozzles and diffusers. So, we again start with the same expression. We have sigma of mi dot. I know there is only one inlet and one outlet, so I am going to remove the sigma right away. Again I should have sigma of mi dot, but there is only one inlet and one outlet. So, I have gotten rid of that. And I have mass conservation. Again the sigma mi dot, sigma me dot, there is only one inlet, one outlet, so I have gotten rid of those. We expect these devices to again operate under steady state, therefore, this must be 0. Therefore, m dot I minus me dot is equal to 0, or m dot I equal to me dot equal to some m dot. It is steady state, so any derivatives with time are 0, anything divided by dt is 0, so this is also 0. So, I have this expression here. In an ideal nozzle, I expect it to be insulated, I do not expect any heat transfer. Ideal diffuser, I expect it to be insulated, no heat transfer through the walls, therefore, this is 0. There is flow coming in here, liquid or gas coming in here, going out here. The nozzle itself is rigid, it does not have any change in volume, there is no piston, nothing. The nozzle does not have any shaft or anything going through it. There is no electrical work, there is no magnetic work, surface tension work, shaft work, displacement work, nothing is there. So, no forms of work in both of these, therefore, this is 0. So, I am left with this expression over here. I have already said that m dot I is equal to m dot E equal to some m dot. So, I can remove this. Since all of these are 0, I can divide by m dot. So, I am left with this. So, I can divide by m dot here. Typically, these devices are fairly small. So, even if it was vertical, there would not be any change in potential energy. If it is horizontal, anyway the height from the ground is the same on left and the right. So, the difference in this, not individually, but the difference in this minus this is essentially 0. So, I am left with essentially the other two terms. So, I am left with these terms. So, I have the enthalpy and specific kinetic energy. So, this enthalpy plus Ke is equal to enthalpy at the exit plus Ke at the exit, which is the expression I get for the either a nozzle or a diffuser. Of course, if there is not much change in kinetic energies, then we would get a similar expression as the throttle. But usually we expect some change in kinetic energy, because the whole idea of this device is to change the velocity. So, we would expect some change in kinetic energies. So, what we can also see is, if I rewrite this, so I have this minus this is equal to exit enthalpy minus inlet enthalpy. So, if the exit enthalpy is higher, so this would be greater than 0, this will be positive, then this must be positive. So, if I had a higher initial kinetic energy and a lower exit kinetic energy, so that this is positive, then I would get this as being positive. So, I have Vi square minus Ve square by 2 is essentially He minus Hi. So, that is essentially what I have. So, in the case of a nozzle, I would expect Ve to be larger than Vi. So, I would expect this term to be negative, which means that this term also would be negative. So, which means that I would have a higher enthalpy at the inlet. In the case of a diffuser, I expect V at the inlet to be higher than the V at the outlet. So, I would expect this to be positive, which means I would also have a higher enthalpy at the exit. That is essentially what I expect to have. We can go to another set of devices, what are called as heat exchangers. We see this in a lot of machinery. Of course, a common heat exchanger which you have at home is inside a refrigerator, where there is something which is cold inside, which is trying to cool what you have, and at the back of the refrigerator you are also likely to have seen something like a grill which is hot and trying to transfer out heat to the atmosphere. One kind of refrigerator is what is shown over here. You have all of these pipes through which some liquid is flowing in this direction, and around the pipes there is some liquid flowing in the other direction, and they are transferring heat between each other. So, this is sort of a schematic of that. So, we have here multiple inlets and multiple outlets because we have more than one fluid. We have one fluid, for example, which is going like this, one fluid which is going like this. So, we have more than one inlet and one outlet. So, the first law for this we can write, but before that if I write mass conservation, I have this, and here I cannot remove the sigma because there is more than one inlet and more than one outlet. So, this is going to remain, and I have the first law, I have heat transferred, I have work done, I have sigma mi dot because I have more than one inlet, and I have sigma me dot. So, I have this kind of an expression. In this device also, I usually expect things to happen in steady state. So, if it is a steady state device, any derivatives with respect to time must be 0. So, these two are 0. So, I have this as the expression for the mass conservation and this as the expression for energy conservation. I have two fluids which are transferring heat with each other, but I expect no heat transfer outside this with the air which is outside. Any heat transfer to the air outside, I expect it to be 0. Between these two fluids there is heat transfer, but apart from this heat transfer I expect nothing else to happen. The heat transfer between these fluids is internal to my control volume or my system, and therefore, that does not feature as heat in our equation, because anything which happens within the walls is considered as internal stuff and does not come out as heat transfer. So, this Q which represents heat transfer to anything outside the system is essentially 0. There are fluids moving inside this. You need to push the fluid through, but any energy to push that is already taken into account in enthalpy. So, there is no other work done, there is no shafts here, there is no change in the dimensions of these pipes. So, there is no electric magnetic work and so on. So, therefore, any work done would be 0. So, I am essentially left with these terms. In many of these cases, what we see is the changes in kinetic and potential energies are small, and therefore, all of these terms would cancel out. So, assuming that that is the case, I can simplify further. If those were not true, I could just use this expression and calculate. But in those cases where kinetic energy and potential energy changes are small, what I am left with is that m dot I is equal to m dot E sigma into enthalpy of E. So, this is what I would be left with in these kind of cases. If I have the m dots as 1, 2, 3 and 4, I can sorry, I can expand this out as m dot 1 H1, m dot 2 H2, and this could be expanded as if 1 and 3 are coming in according to this sketch, and 2 and 4 are going out according to the sketch. So, 1 is coming in, 3 is coming in, 2 is going out, 4 is going out. So, m dot I is essentially m dot 1 which is coming in plus m dot 3 which is coming in, and this is 0. So, I can take this to the other side. So, this is essentially the mass conservation, and this will be the energy conservation for this kind of a device. So, we have seen that we can write the first law in the general form, which is this. In many of these cases where we have specific devices, we can cancel out some terms and get simplified expressions which are useful for these devices. So, in a sort of a short summary of what we have just looked at, in the adiabatic sorting process, assuming that it is adiabatic, therefore, this is 0, there is no work done, assuming that changes in potential and kinetic energy are small, we got this. In rotary turbines and compressors, assuming this is 0 and assuming these changes are 0, we got this. Similarly, for nozzles and diffusers, we had something like this, and for heat exchangers, we had this. So, we assume Q dot is 0 in all of these cases. Here we also assume that W dot is 0. We have assumed in all of these cases that they are steady devices. In some of these cases, we assumed single inlet and outlet. In these 3, we have assumed negligible potential energy changes. We have assumed negligible potential energy and kinetic energy changes. Actually, we do not individually need them to be 0, but we need changes to be 0. So, assuming all of these are 0, we have got this kind of an expression. So, we have some simplified versions which we can use in order to solve problems. So, we are going to stop here for the moment. So, thank you.